In this video, we're going to look at power functions and polynomial functions. Now, we're really going to focus on power functions as a way to discuss polynomial functions, but we kind of have some experience. So first, let me go ahead and tell you what a power function is. So a power function is a function that can be written in the form f of x equals x to the p. That's a very sad looking p. Let me fix that. P is the power of the power function or the exponent. X would be the base. So functions are in this form. Now, technically, it could have a constant out in the front. So what we want to look at then is what power functions have we already seen? And let's focus in on the toolkit functions. Actually, the majority of the toolkit functions are power functions. So for example, f of x equaling x squared works, x cubed, that works. Technically x, because x to the 1, right? So the identity function works. The reciprocal functions, the 1 over x, technically is x to the negative 1. So that's a power function. 1 over x squared would be x to the negative 2. The square root function can be written as a power of 1/2. It's kind of a sad 2. Let me fix that. Same with the cube root function. And then technically, though I'll call it the honorary one, that would be the constant function. And the reason the constant function can be thought of as a power function is technically that can be written as c times x to the 0. And x to the 0 is 1. So any number by itself can be thought of as being in this form, since we could write it as that number times x to the 0. I kind of don't like that, only because the c is in the front and we have no c in front of our power function general formula. So I'm not a big fan of that, but the book does include it. So I figured I would go ahead and include it when we made this list. So the only one that actually doesn't work, according to the book, is the absolute value function. Okay, let's talk about characteristics of the power function. So let's start with this. What I like about this is they graphed these 3 power functions. The one we know, x squared, and they graph 4th and x to the 6th. So all 3 of those are there. And you kind of notice they look very similar. They're all this kind of U shape. What I can tell, though, is that x to the 4th and x to the 6th are kind of getting like a flatter bottom, right? It's almost like the U is flatter when you're close to the vertex, and then they can shoot off a little bit quicker than x squared, which makes sense because they're higher power, so those numbers would be getting bigger faster. But what we want to look at is something called the long run behavior, and we're going to kind of use this later on. So the long run behavior is this idea that we're interested in what's happening when we look at the behavior over time. Okay, so when I'm looking at this behavior over time, what I'm seeing is that the graph of the function, as the input values take on large negative values, meaning that the x's are going to the negatives, we're seeing that the y values are going to the positives, right? So that would mean that f of x would be taking on positive values. Now, we write this very specifically, and this notation is what we're introducing here in this box. So the behavior of the graph of f of x is the input values take on large negative values, which we will express as x is going to negative infinity, and positive values, that would be as x goes to positive infinity. So what I'm noticing on this graph is as x is going to negative infinity, so that means we're looking at values going this way, our functions are all also going to the positive infinity values. As we look at them going in the positive direction, again, all of the y values are shooting off into positive infinity. Let's look at these other functions or power functions. In particular, now we're kind of looking at odd values, okay, like odd numbers for the exponents, x cubed, x to the fifth, x to the seventh. You'll notice all three of those look very similar, even more similar, except when it's closer to the origin, the x to the fifth and x to the seventh are kind of flatter, and then they shoot off just a little bit quicker than x cubed. So let's look at the long run behavior here. As x goes to negative infinity, the y values, which I'm going to call f of x, are going to negative infinity. As x goes to positive infinity, the y values are also going to positive infinity. Let me come back up here and write that up here. I kind of said it, but I didn't write it. So as x goes to negative infinity, f of x is going to positive infinity. But that's also happening as x is going to positive infinity. So I could say that as x goes to plus or minus infinity, both positive and negative infinity, our y values are shooting off to very large positive numbers or positive infinity. So let's kind of apply this to a new example. So let's describe the long run behavior of x to the 8. So that's an even function. An even power. So that makes me think that it's going to probably look similar to these graphs up here, which would mean then that as x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x is still going to positive infinity. Okay, so this graph here with an odd power, I'm going to kind of think it's maybe going to look similar to these graphs here with the odd powers. However, it does have negative in the front. So a negative makes it reflect. We know what that does. So instead of it climbing up like this, it's going to go the reverse direction. It's going to go like that. Okay, so then that would mean that as x goes to negative infinity, f of x is going to, positive infinity. And as positive infinity, f of x is going to negative infinity. So the fact that the powers have odd numbers versus even numbers affects long run behavior in the graph, what we kind of expect to see. So let's apply this understanding to polynomials in general. So first thing we're going to do is introduce a little bit of terminology for polynomials. So a polynomial is a function that can be written like this. F of x equals a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, plus. So each term is decreasing until we get to a squared x squared, a sub 1 x, and then a sub 0. So it's this pattern that we have these numbers matching with decreasing powers. Each of those numbers in front, a sub whatever, a generalized way of writing that would be a sub I. That's how we say whatever in math. A sub I are what they call the constants, and they're also coefficients in this polynomial. They can be positive, negative, zero, whole numbers, decimals, or fractions. A term of the polynomial is any one piece of the sum. So that would be anything with an a and an x. Here, I'll do that in terms of sub I notation. So that's generalizing it. I don't know which one I'm referring to. I'm referring to the ith one. Okay, degree of the polynomial is the highest power of the variable that occurs in the polynomial. So whichever number is the highest, that's the degree of the entire polynomial. Now, typically, we write polynomials specifically so that the leading term, the first term here, is the highest power. That's why it starts with n, and then it goes to n minus 1. So that's less than n, right? 1 less than n. And then it keeps decreasing until we get to 2, 1, and then technically 0 right there. Okay, so it's decreasing as we go down. And actually that's said right here. So the leading term contains the highest power, term with the highest degree. The leading coefficient is the a sub n in front of there. And with the definition of leading, we often rearrange polynomials so that the powers are descending. So just for an example, an example would be to show for descending, this would be an example of descending polynomial. All right, x squared plus 2x plus 1. Because the x squared is the highest power. Sorry, I should have put like a function notation in front. Sorry. X squared plus 2x plus 1. So that's the highest power. And then each next number is descending. Here, let me do one more. Let's do g of x equals 8x to the 5th minus 3x cubed plus x. That would also be an example of a polynomial written in descending order. So the powers are going 5, 3, and then technically that last power there is a 1. Okay, let's use that in an example. Let's identify degree, leading term, and leading coefficients for these polynomials. So first thing I want to do is make sure they're in descending order. The first one is not. So I'm going to go ahead and rearrange it. So negative 4x cubed plus 2x squared plus 3. Okay, so degree of this is going to be 3, the highest power. The leading term would be the negative 4x cubed. But the leading coefficient would just be the negative 4. Okay, so let's apply that to the next one. So for g of t, they happen to have that in descending order for us. That's nice. So let's see, the degree then would be 5. I'm going to go ahead and call this LT for the leading term. So the leading term would be 5t to the 5th, and the leading coefficient, LC, would be 5. That 5 in the front, I'm referring to this 5 right here for coefficient, and this power would be the degree, just so we're clear. Okay, so last one here, h of p. Okay, that's not in order. Let me put it in descending order. So negative p cubed first, plus 6p minus 2. Okay, there we go. Degree would be 3. Leading term would be negative p cubed, and the leading coefficient would be, well, in this case, negative 1, since I'm not seeing anything, but I can assume that there is, in fact, a there. All right, so let's apply the long run behavior that we talked about with power functions to polynomials and how it works. For any polynomial, the long run behavior of the polynomial will match the long run behavior of the leading term. So for this example here, what can we determine about the long run behavior and the degree of this polynomial? So I can already tell, because one end is going to positive infinity and one end is going to negative infinity, that this is probably going to be an odd power. So minimally, I should be looking at like x cubed. Okay, so since as x goes to negative infinity, f of x is also going to negative infinity. Oops. And as x is going to positive infinity, f of x is going to positive infinity. So that's a hint. That's not chance. Odd powers go to opposite sides. One side is usually going to positive infinity. The other side is going to negative infinity. All right, so that's an odd power. Now, other than that, that's all I got, because I don't know much else. I mean, maybe it looks like x cubed, maybe it's an x to the 7th. I don't know. I'd have to kind of dive in a little bit deeper, but it does help me kind of know that it's going to have that basic shape when I'm looking at these polynomials. And we're going to dive in further and more specifically about how we could figure out what the leading term would look like in this type of polynomial.